Thank you. Thank you. The talk's over. Thank you, everybody. I hope all you've been drinking a bit, because this is good. This is going to be a rough talk. This is a very technical talk. So also already we have corrections, right? The title of the actual talk is Return to R14. Someone who submitted the talk got the title wrong and put the wrong register in there. That person was me, so I fucked up. But it's corrected here, so you know, the reason we put R14, you'll see why we use R14. You probably know why we use R14. Yes, well, Bill's ruining my talk already. Let's go. All right, so, well, you're not allowed to answer questions for stickers. So, my name's Phil Young. I go by Soldier of Fortran. Do I know how to write any Fortran? No. I do mainframe security research. Here's a fun game. It's been a long day. I want everyone to stand up. Okay. And then sit down if you used a mainframe in the last, let's say, 48 hours.
Like directly?
I mean, sorry, let me rephrase. Stay standing if you use a mainframe in the last 48 hours.
Directly?
I'm not being very specific. Yes. All of you should have stayed standing. Like,
I used a credit card.
if you used a credit card to pay for anything, even if you did it, you know that scene in Hackers where it's like there's mainframes processing shit all the time? That is true. All of your information goes through all these mainframes all the time. Not even like if you flew, if you got gas, whatever, mainframes are involved in some capacity, right? So I do mainframe security research as my job. I do that for NetSpy. I am the director of mainframe pen testing there, where we do mainframe pen tests against your LPARs. I'm not going to use too much mainframe lingo in this talk, because it's APM, and people have been drinking, and B, it doesn't really matter for the sakes of the buffer overflows. But anyway, so we do like network, RACF, all that stuff, okay? So that's my job. The reason we do that is because you would not believe the shit I have seen in the wild on very important systems that we all rely on, okay? I used to work for a bank, and I found a really bad thing, and my wife said, hey, should we be banking with this bank? And yeah, that's what I still do, because I was like, well, I fixed it, so it's the safest one now. Yeah, well, anyways, they're trying to bring me back in. Alrighty, so I am a big supporter of the open source philosophy, which is not really a thing in the mainframe community. It's getting better. It's getting much better. But I gave this talk at Share, and I had to put a slide about like all my tools are free, because like literally I'll talk about a tool at that conference and they'll be like, where can I buy this tool? And it's like, it's on GitHub for free, right? Yeah, it costs as much, well, a GitHub license. So
It's in ChatGPT now.
yeah, it is definitely in Chat. I feel so bad for ChatGPT reading my shitty assembly. Man, oh man. Anyways, so I'm big proponent of open source software. All of my tools, now this is a long talk, so I'm not going to show you all these tools. I'm just going to show you two of them. I was hoping one of the authors for the other tool was going to be here. That's why I put it specifically in this slide deck. So CatMap is written in assembler assembly, and it maps out the file system and tells you what files you have access to and your level of access. This is important because A, it's very fast. I've run it on huge mainframes, and it took 30 minutes and created like a 1.6 gigabyte file of just this, right? So yes, and then there's a lot of data to process and a lot of things to go through. But there's not like a find command on the mainframe. So we have to bootstrap our own tooling. The other one that you would be shocked how often it works is, how do I go egress from the mainframe to like something in the cloud, an AWS host or something, right? Because typically a lot of mainframes were set up before the internet existed, and then they implemented some routes to the mainframe for business, and all those people have retired. So when the ticket comes in, it's like, hey, you should probably not do this. They're like, we accept the risk. We don't know what it does. We don't know why it's like that, but we don't want to get yelled at if it breaks. So, yeah, it is. The mainframe world is fantastic. So this tool was written by Owen Henty. He's a local. It It's written in Java specifically because we can control the timeout on a TCP packet in Java using older syscalls. All the other languages, you can't do that when you're using, and I really didn't want to write TCP IP in assembly. So really, we're just doing a syn scan as fast as possible against a host that has all the ports open. Yes, my beverages have arrived. My water has arrived. Okay, so mainframe buffer overflows. Who figured this out? It was not me. Sorry, there's a leprechaun in the front that's...
I disagree. You figured it out.
I definitely did not. And that's not true. This is 100% true. I did not figure this out. It was a different person. So I run a society of like-minded individuals called the Mainframe Hacker Society. And the Mainframe Hacker Society, the rules are you either have to give a talk. We have a member in this room if they're willing to divulge that they're a member. It could be anybody. So the only way to become a member of the Mainframe Hacker Society is to give a talk or publish tools. And if you publish tools, then you have to give a talk on your first meeting. Members have to also give talks or participate in the meetings frequently. So we meet once a quarter, and we'll tell someone like, hey, we haven't heard you talk for a while. It's time to re-up. Right? Can be on anything, but you've got to talk or else we'll boot you. And we've kicked people out. So anyway, or what will happen is some random person gives a talk somewhere, and then I show up in their inbox, hi. Thank you for giving a talk about mainframes. Welcome to the club. Here's your membership to the club. It's a super chill Slack. There's like 15 of us. So that's true, right? That's true. Yes. So Jake LaBelle gave a talk at DEF CON, the canceled one, about surrogate chains. And that's spelled correctly on the mainframe. Okay, that's not a typo. So he gave a talk on that. Then I reached out to him and said, hey, welcome to the family. Now you're a member of the Slack. Enjoy being a member. And then he just figured it out. He was talking to Chad and some other folks about, hey, I have some background in this and that. But he's the one who figured out how this works on z/OS, which is like the main flagship mainframe operating system. And then after he figured that out, he then moved it into MVS, and you'll see why that's important in a bit. He used to work for like a consulting firm, and then he left, and now he works for Rocket Software, where he does pen testing and system integrity testing. Right? That's his. So he does all this kind of cool research as his full-time job now, which is awesome. Public domain mainframe. So there is a statement on a website. So back when they were inventing the operating system, because before like mainframes, there was no operating system. It was very like, hey, you weave the code into the magnets themselves kind of thing, right? So they created all this software, especially for NASA, but they didn't copyright it. So it's public domain. So we have the source code to the first and to OS 370 essentially. So that means we can run our own sort of mainframe. I mean, is it as good as today's modern day mainframe? No, you get only 24 bits of addressability versus, I told you this was going to be a heavy talk, 24 bits of addressability versus 64, right? So 24 bits is not very much for addressability. But what's really cool is there's a whole community around it. There's about like 3 distros now. 2 of them are it's one person who runs it. It's very closed. As the open source nerd, I do not like that model, so I created my own. It's essentially like the Gen 2 of mainframe. You run a Python script, it builds the whole mainframe environment for you from like virtual tapes. And then you can just deploy it in Docker, and I use it for all my trainings, and I use it for all my workshops. It's public domain, so I don't have to worry about getting hassled by a certain company. But also, B, it means you all get to benefit from having access to it, right? Because that was the hardest thing when I was starting out, was just getting access to these things. This is what it looks like. This is the login screen. It looks very similar to the rest of mainframe stuff, right? It's got ISPF, it's got JCL. But what's cool is you can use it. So I use it to build and test tools in GitHub. So this is all GitHub actions that I'm running, and it gives me a result back. And so I can push code up, test it, and it's all automated and all that stuff. Cool. I'm not here just advertising this thing, right? Like it sounds cool, but what does it have to do with this talk? Well, the rest of this talk is going to be based on a Docker container that comes with a full training built in. So if you are like, oh, this is cool, or I got lost 20 minutes in, I wish I was paying more attention, you don't have to worry about it. You can just run this Docker container, connect to, like, I think port 8080, and it's running a wiki that steps you through everything we're going to talk about today, and examples, and JCL, and has you write all this stuff and write the overflows for you. It's very, very cool. Now, who here is a mainframe, like who here has done any work on mainframes? Not in the last 4 hours, I mean ever, right? Who here has written like assembly for the mainframe, right? Less hands. Isn't it fun? It's super fun. So there are 16 general, this is what you need to know for this talk, basically. There's a lot more going on. There's like 1,000 pages books about this, right? But for this talk, there are 16 general purpose registers, okay? That's it. That's all you get. Why so many? I don't know. You have what's called the program status word, right? It's important. The only thing that matters about the program status word is the last 4 bytes is the address of the instruction that is currently running. So that's where in memory that instruction came from. JCL, who here has written JCL? Yeah, it's fun, right? It's basically like a Docker file, right? That's all essentially what it is. It's like a Docker file. You set up environment variables, and then you run some programs, right? That's pretty much what it's like, and it's headless. Save area. Let's talk about the save area for a second here. So you're a program that you've been written, and you've been assembled, and linked, and you're waiting. And another program calls you. The expectation is when you return to that other program, you put all the registers back the way they were. So when you get called, all the registers are whatever the previous program was doing, right? There's no cleanup before they call you. So your job is to save the current registers, all 16 of them, into a space in memory, do your business, then move all those registers back to the way they were, unless your program says like, hey, register 1 returns this, right? But it doesn't do that. Yes?
What if the program crashes?
That's on you for being a bad programmer. So the question was, what if it crashes? And that's on you. So, look, it's IBM, it doesn't crash. I don't know what you're talking about. But the important thing to know is you have to save that somewhere in memory before you do your stuff, okay? The other thing that's really important is the sort of standard is register 14 has the memory address of where you came from. It is for all intents and purposes the return pointer, okay? It's not called the return pointer, it's just register 14, right? But that's where, so when you call a program, it knows where to go back. So if we're doing a buffer overflow, the plan is overwrite the save area so we can overwrite register 14 in memory. So that when the program goes back to where it came from, it goes back to a place we control, right? That's all we're doing. So with me so far, this is like standard buffer overflow stuff. So this is what the rest of the talk's going to look like, right? It's for the next 45 minutes, for the next 3 hours. Yes?
So just to confirm, all of this mainframe stuff, it's written in memory in secure C programming language?
No, it's actually mostly written in COBOL and other languages like that. But there are vulnerabilities that exist. And it doesn't have to be C. You'll see in a second a program that's not C. That's vulnerable. So, three parts here. They're going to build on each other, and they're going to get more difficult as we go. The best one, my favorite part, is number 3, because remote code execution becomes very challenging. All right, so who here knows what a buffer overflow is? Good, so I don't need to go through these 2 slides, right? So 1, 2, right? That's a buffer overflow. That's what it says. When it kernel panics, it says, oh no, too much data. Look, this is the nice version. I was going to go a little anime with this, and I decided, we'll keep it family friendly. Okay. Let's talk about exploiting a C buffer overflow on a mainframe. All right, so this is my favorite part. We have a game that I like to call, What's That Overflow? All right, I have prizes. I legit have stickers to give out. They're like Supreme stickers, but they say mainframe. So they're legally distinct. All right, where in this program is the buffer overflow? Okay, new rule for when I ask questions. Wait for me to call. Someone said it first somewhere over there. Right here? Yes, come on up. The problem is now you got to come all the way up for a sticker. I'll make you my sticker person. Yeah, there we go, yeah. Yeah, I should have played the song. Let me load it up. Alrighty, so it's obviously, it's this part here, right? Right? It's not memory safe. Like, that's the problem. And so we only create a buffer of 150 bytes. So if we have more than 150 bytes, we'll see what happens. I mean, names can be however long we want. There, you know. So anyways, is there a way to turn down these lights a little in the front of the room? Yes. Because there's a lot of black screens. What's that?
You're asking where the buffer will go on this page?
No, this is the program running on the mainframe. I'm just asking them to turn down the lights a little because it's like it washes out and it's all black screens. The mainframe, it's like when you watch a movie, like a hacking movie, and they talk about mainframes, this is what it looks like in real life, right? So anyways, so we call our program. That's how you execute programs on a mainframe. You call them, you don't run them. And then so I type in my handle, I type share, and it says wake up, share, the matrix has you, blah, 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 right? Very, very standard. See, that's what the program does. A couple of things to know that are important about C programs on the mainframe. They require std in and std out, right? You don't have to do that in Unix. It's all done for you. You have to do it in the mainframe space. So when we're on the mainframe, so I'll walk over here. When we're on the mainframe, if you look here, right, there is, did this stop work? There's a term file that goes to std out and a term file that goes to std in. So that's how the C program communicates with the terminal that you're connected to, right? That's what that means there. Oh, here we go. This did stop working, right? So if we're going to run this in JCL, because we need to run in JCL, we're going to have to pass it those two, for lack of a better term, environment variables. I don't want to get too mainframey. Okay, so first we're going to run a test, okay? That's JCL. Remember when I said JCL previously? This is what it looks like. The creator of this gave a talk at the Computer History Museum where he just roasts JCL for like a good half hour. And he invented it. Yes.
What year did he die?
He might still be alive. I should look. That's a good question. All right, fair. That's the only one you're getting. Yeah, from now on, if you're going to heckle me, it better be much better than that. Alrighty, so this is JCL. Like I said, it's a job control language. The important thing to hear is the data definition, the two Ds, right? Yes, I am keeping this family friendly-ish. So anyway, for the rest of this, we don't really need to care about the job card, right, which is at the top of the screen here. We can get rid of the job card, and I'm just going to highlight what's important about the JCL, right? This line is what runs our program. Remember in TSO we had to call space the program name, right? Well, technically we're calling the folder and then the file in that folder. That's what this is doing, right? This is executing the program hello, okay? That's very easy. And then how does it know where to find the program? Well, there's a path. For those in the back, you might need to stand up. But at the very bottom is the path that we're using to run that file, right? So it sits in that folder. And so this is still the same test. So we're going to do the same thing we did. This is standard out. This is just going to the syslog. And then this is our standard in. So instead of share, we're just putting testing. And if we run this, it'll be the exact same output just on the syslog. Okay? So I'm not going to show it again because I don't have time. Now we're going to do a buffer overflow. We have a data set that is 400 bytes wide. Okay? Now remember, who remembers how wide our buffer was in the program? 150, right? So we have repeating LGBT, LGBT, LGBT forever. Okay? So instead of running the program like this, we're going to change that standard in to point to that file that we're going to throw input into that C program. The problem is it's going to crash, and we need to keep track of what's in the crash. Like we need the kernel panic stuff. But this is headless. This is batch driven. So you fire and forget, and you get your responses later. So we need to add what's called, and this is not a joke, a dump. Okay, so we have to have a system dump on the system, right? So that's what this is. So this is a dump of memory and all that stuff that happens when the program fails. This is for every program, right? So every program, you run it. If you put this variable in your JCL, if it crashes, it takes all memory and everything and dumps it into there. So when we run this program like this, we get this return code. Does anybody know what an abend S0C6 means on the mainframe? That sticker, like if someone knows that, that's a sticker, yes.
Is it abnormal ending?
Well, abend means abnormal end. That means the program crashed. But the 0C6 means something specific happened in the program. Yes?
Something bad happened.
Very true. Yes. Very accurate. Very in-depth response.
Access violation.
What is it?
Access violation.
Close. You're trying to access a place in memory that doesn't exist.
That is an access violation.
Yes, that's an access violation. So you got lucky with the guess. So this is what it looks like in the dump file. So we have a dump file. Yes, question?
Can you keep that back up while I Google it?
You can Google it right now. It's 0C6. All right, so this is, can someone tell me, does anything look familiar from a previous slide in here somewhere? Anybody? Anybody? I'm being obtuse on purpose.
LGBT shows up somewhere as that.
So this is remember the PSW? Remember I told you the PSW contains the address. The last 4 bytes is the address of the instruction we were running. When it crashes, it gives you the PSW at the time of the crash. And if you look right here, well, that looks awfully familiar. That looks like the last 3 bytes of this, which is just this. So we now know that we can control where the code is executing in memory, maybe. Right? We caused the program to crash, and it tried to go and tried to run something in memory at address C7, C2, E3. Okay? Everyone with me so far? Yeah. It's going to be real rough if you're not. All right, good. Right, so we caused the program to crash, but where in those 400 bytes did we cause the crash? That's what we need to figure out. So we use a pattern like this, AAA, BBB, CCC, and we run the program again, and we crash it. This time, if you look at the program status word, you will see that it is now C7, 7C, 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 which, if we open up our file in vbindiff, for those who didn't know, vbindiff supports EBCDIC files. That's why I like using it. So if you look way down here at the very bottom, 7C, 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 that's where we can control the return address. Right? So what's happening in the program is it loads up register 14, but register 14 has been overwritten in memory, and it contains this whole file. Right? So somewhere in this file, it overwrote register 14 with C7, C7, 7C, 7C, and so that means we can control where we're going next time. So now it's time to write some shellcode. The first thing we need is the address of where our buffer starts, because where are we going to jump to? So it's in the dump, which is great. So we can just look at 0B4, 0A0, right? And that's C1, C1, C1. That's the beginning of our file. So now, what was it here? A0, but here I'm going to AB. Does anybody want to guess why? I am yes, because I need to be here. I need to start here. Because it's full word or half word based. Like you have to be on the thresholds for your program to run. So we couldn't start here. So we skip all these bytes and we start over here. So this is what's happening, right? We have our regular program. It overwrites the save area. We've overwritten the save area. And now we go back to the beginning of our buffer instead of returning to the actual calling program. Okay, but we need one last thing, right? So we can control the register. We can control the pointer. We can point it to memory. Now we need some shellcode. This is definitely sticker worthy. Take this, take a screenshot, feed it into ChatGPT, and tell me what it says. Don't do that. Oh, you can do it. It's fine. I'm just curious if anyone knows what any of this does. This is machine code.
Are we allowed to ask for clarification in the assembly language architecture
It's, I know I have a cup. I'll finish this and then I'll get some.
Can we ask for clarification regarding the assembly language?
It's Z architecture.
It's what?
Z architecture, Z architecture. So I'm from Canada, so it's Z architecture. It's Z architecture. It's its own thing. And in fact, this isn't even Z architecture. This is like MVS architecture.
It's not x86.
No, it's not x86. It's not ARM. It's its own thing. That would be way too easy. Come on. Okay, so no takers, no guessers, except for Bill Beers, because he probably knows. When I gave this talk at Share, when I tell you I put this slide up thinking maybe one person would have to work it out, literally on the screen, and one guy goes, and he's like, oh, it does this. And I was like, dude, you're stealing my thunder. I told him, you'll just come up and talk about this slide for a bit. That's what all that shell code is doing, okay? Easy, understandable, right? Everyone gets like what's happening here, obviously. Okay, so okay, look, this is not my first talk about mainframes to people who don't know mainframes. So, everyone, first thing, you're taking a register, load register 1 with the address stored in register 15 plus 8. That's all this is doing, right? So this is your addressability. SVC 35 says write to the operator console, right? So we're just popping calc essentially. That's essentially what we're doing is we're popping calc, okay? We're print whatever is at the address that's in register 1. That's what that SVC does. SVC 3 says end cleanly. So when whatever happens, when you end, the return code is 0, okay? Because sometimes if you don't do that, you return with your own buffer, but then it keeps going down memory forever, right? So we exit cleanly, and then we have the length of our text, right? How big is the text to print plus 4, and then we have our text that we're gonna send to the console. That's the whole overflow. So now our exploit looks like this. This is our exploit, okay? We have our pointer that points back up to our code up here that starts 4 bytes in from the beginning of our buffer. And when we run it, we get this. Can anybody tell me where they see in this huge screen? This is why I had you turn down the lights because it's a little dark. Yeah, I mean, you can see it, right? You can see right at the top here. We hacked the mainframe, okay? If you do the Docker container, you too can get this far and say you've actually written a buffer overflow. Yeah, don't do this on a work mainframe. You will get in some major trouble unless it's sanctioned, right? All right, let's look at exploiting an assembler program, right? Instead of a C program. Everyone knows C is not safe, but mainframes aren't hackable, right? So let's look at assembly. Now it's time for another round of what's that overflow? Tell me where the overflow is in this. You'll get stickers.
And are you looking at a particular line of code when you're asking this one?
No, the whole thing is just the problem. I'll step you through it step by step. I'm not going to be like, anyways, moving on.
I'm going to guess it's the LM line.
Which line is that? You're talking about load memory?
R12, say.
Okay, so, like I said, the whole thing is the problem, yes.
I'm leaning towards the first line on top, get IDCD, and
Yes, you're absolutely right. So you'll get a sticker because you're the closest guess. It's the first line, but it's really a combination of all these things. So watch this. First, we have a thing that loads. So you give it an environment variable, a DD, right, called NDCB. It's declared down here as a file, right? So it's going to load the file. What it doesn't specify is only pull 80 records. Because mainframes typically, the expectation is the files are 80 records wide. That's typically how they work, right? So like some programmer just made an assumption, like, why would anyone run this program without data that I built? Yeah, why would anyone need more than 80, right? So yes, so PEP8 works on a mainframe. But this was probably, programmers don't write things to handle all cases. They sometimes just write it to get it out of the shop, right? All right. So the next line, which the person called out here, this loads a line from that file. There's no checking here to make sure it only loaded 80 characters. It just assumes, right? And then the next problem, so that's the in area. That's where it goes, right? So we open up that one line, and it goes here. And if you notice what the length is on this line, it's only 80 characters long. It's only 80 bytes. So we have a storage in memory that's 80 bytes long, but we don't do any checking to make sure what's coming in is 80 bytes long. And then we then return, so as the program's running, right, we load from memory the registers, right? Remember, we have to return the registers to the previous state and return to register 14. That's what this is doing. Loading the registers, returning to register 14. That's what that does. So now we're going to branch back to the calling program. But the problem we have is our save area is underneath that buffer area for our file. So if we have something that's longer than 80 characters, we overwrite the save area. And therefore we can control register 14. That's the whole game. That's the whole thing we're doing, right?
Would you overcome the issue if you flipped the
Yep.
and saved the other?
I mean, if you flipped it, you would overcome this issue, but you would have other issues because now you're overwriting memory you don't own, or you're overwriting stuff. Yeah, it's just not best practice, especially in assembly. You should be controlling what you're doing in assembly. All right, so when we have, so they're declared as record length 80. That's how you declare a file. It just assumes that's happening. Okay. All righty. Who here has used a De Bruijn pattern before? De Bruijn patterns. Yeah, a handful, right? So,
Anyone who's used pattern offset or pattern?
yes. Anyone who's used it in Metasploit, but I mean purposely, like someone who's like doing research. So, it's like my question, like who here's used a mainframe? So, this makes finding, instead of having to do that rigmarole where we were like, oh, we got an A, B, C, D, all these things, now we can just feed this into any program and we can get an output and tells us exactly where in that file we need to change the return. Yep. So we generate a De Bruijn pattern, right? And we take that, so now we're going to call that program that's exploitable, we're going to call it with our De Bruijn pattern and 1,000 characters, right? And we know that this file can fit 1,000. So there's a thing you need to know about mainframes. There's no hand-holding. So when you make the file, you have to tell it how big the file is. So you have to be like, I need a file that's 4,000 characters long and 700 lines, right? Did you need more? Too bad. Make a new file and copy that stuff over. Okay, so we submit the job, right? We're just running the program. That's all this is doing. We're going to submit the job. And notice down here, we have the De Bruijn pattern, okay? So we put it in a file. We put it in that one file. That's what this was doing, right? So this step, put it in that file, and now we're calling the program with the contents of that file. That's all. And look at that. We caused a system dump, just like previously, and if we look at the return address here, right? This is the address in memory that it was supposed to be in. If we look at that, we know it's in our De Bruijn pattern, right? Because it was trying to return here to register 14. Everybody with me so far? Yeah? So if we look here, right? Because here's what happens. Sometimes when you exploit a program like this, it keeps, maybe you just randomly jump to an okay place in memory that had something that looked like an instruction. So it's going to keep going, right? So what happened here is it probably kept going for a bit, but we have register 14 right here. That's the contents of register 14. It's in the dump. The dump tells you register 0 through F, here's the contents, right? So if we look in our De Bruijn pattern, we look for F8, C1, it's right there, right? We can just search for the hex bytes, and it goes straight here. Now, if we go in memory, we have to go back in memory to find out where we need to go. Just like we did before, right? Everyone's on board here? We're doing the same thing we did last time. It's not really special. We find the memory. Okay, now we need to write some shellcode. When we wrote the last shellcode, we did it by hand. we wrote machine code by hand because that's what you do. That super sucks. We're not doing that. I don't want to ever do that again. So we're going to have the assembler create the shell code for us. So here is our eye catcher. Here's another eye catcher. When we assemble this, we can find those eye catchers in the hex dump and then just copy our code here. Right? That is our shell code. We then paste it into our De Bruijn pattern in a hex editor. Then we submit the code. And look at this. Perfect, right? Everybody sees where that is? Yeah? I zoomed in for everybody. Notice how there's an A at the end? No, there's an A. Yes, it's because somebody, when they were making these slides, screwed up. And when they copied this, if you'll notice, I forgot to copy the exclamation point. And the shell code itself, the shell code itself is pulling this many, like hex 10, yes.
First of all, I'm sorry. Second of all, what year did De Bruijn die?
I don't even know who that person is.
De Bruijn? Did I pronounce it wrong?
It's De Bruijn. I looked it up. They have nothing to do with mainframes. They're like a computer science researcher. So maybe. You can try calling them.
You don't even know if they're dead or alive.
No, I don't. Sorry, for those wondering, I don't keep track on the livelihoods and if they're dead or not of all the mainframe people or all the computer science majors in the world. Just so we're clear.
Okay.
Just for those who don't know, Adrian last year called a number on one of my slides to a Rally mainframe company. He died in 12. There we go.
For the group. Yeah, but Heather had my back. Yeah. Did she? Or is she the one that's telling you to fuck off? No.
He was 93.
Are you even alive, Adrian? No. Sorry, sir.
You got keep going. It's fine. This is what people came to see. We done? All right. So, can we use? I love all of you, everyone here, and on YouTube. So, can we use this to do PrivEsc? Almost. In the mainframe world, programs are what are called APF authorized. And an APF authorized library is another term for folder. And an APF authorized folder, any program that's assembled and linked with AC equals 1 is allowed to basically go to ring 0. So if you have write access to any of the APF authorized libraries, I can't tell you how many pen tests I've done where I have that access. Just straight off the bat, my pen test is over, and it goes from a pen test to an audit at that point, because I've full ownership of the entire environment at that point. So we don't have APF authorization with this program, but we just happen to find a program called RBauth that exists that when you call RBauth, you pass it a program to run, and it will run that program as authorized. So let's use that to do, yes, question?
Is RBauth built in, or?
No, that's a program we wrote for this demos, but if you know what you're doing, there are other programs like RBauth that exist on ZOS that you may, and that sold by vendors, installed by the company, whatever, that do this. And you can use that to your advantage. Yes, Bill?
Years ago, most shops had an SVC that was a user SVC that dropped them back into supervisor state. You can find that.
We don't have time to get into SVCs, Bill. There's a whole talk at Black Hat about SVCs if you want to get more info by Chad. It's a great talk. So we're going to use this JCL to call our program. Now, doing PrivEsc, doing a WTO, like a calc privileged, that doesn't matter, right? That doesn't really do anything. It doesn't really demonstrate you could actually do anything. So what we're going to do is we're going to access a file called White Rabbit, right? And we're going to do this by using RBauth to call OpenTest, to overflow the buffer in OpenTest, dump the contents of White Rabbit to the screen with a cat, essentially. And so we're going to spend. Any questions about the code? So this code, I know, great. So this is not supposed to be illegible. This is all the assembly you need to generate the shell code. And if you do the Docker container, you can do all of this on your own. Then we have the shell code that was generated by the assembler. And then we just use this JCL, and that looks like shit. So here we go. So we're going to look at that job that we're going to use to submit and what's going on in this JCL. Because there's a lot, this looks awful. Especially, I see a face, I see someone in the audience who's like, ugh, it's rough. But when you get used to it, you can kind of read between the lines. But what's important here is we're running RBOF to run open test, like I said earlier, right? That's what that's doing. This is our overflow to open test, right? Then we're going to cat, that's what IAB generator, IAB generator moves files around and stuff, but we can use it to essentially cat a file to the syslog. That's all this is doing. All this JCL is doing that. So we're going to overflow the buffer. We're going to get privileged with our shellcode, because the shellcode does. And then we are going to access a file we do not have access to otherwise. That's what we're doing. And we know that it worked because, I'm not going to go back. In the shellcode is a message that prints on the screen saying all files have been written. So here we go. We exploit the buffer and hi and a bunch of machine code, because that's what the actual program's supposed to do, is it prints the first 80 bytes of a line, right? And then we have this, write incomplete. We did it. So that's a privesc now. Let's talk about the fun. So those ones, easy. Those were easy mode. I hear some laughing. Those are so easy. Now we're getting into like mainframe hell. So I see someone giving out shots. Take a drink if you want to, because it's going to get real rough in a second here. So on MVS, there is an FTP server that was written by the community. This is not a product from IBM. It was written in C by the community. It has a buffer overflow in the authentication. So when you put in a user, if that user ID is longer than a certain number of, say, 150 bytes, you're in buffer overflow time. This is a CVSS 10 score problem for the FTP server. It's been fixed. Jake fixed it, so don't worry. If you're running this Docker container, it's all been fixed. So the problem is we have to deal with something that I already mentioned it once, but now it's going to be a real thorn in our side. We now have to dealing with EBCDIC.
Which is why B was CB instead of 42.
Exactly. So that's why when you were looking at all the bytes and it was like, I don't recognize any of this ASCII, it's because it was all written in EBCDIC. Why? IBM invented ASCII for the computers and then said, no, cards use EBCDIC, we're going to use that for our main product. So nothing else speaks EBCDIC except mainframes today.
Thanks,
That is some legacy stuff. Okay, so now it's our last time to play the game. So this time I'll do hands up and you get a sticker. Thank you. This is from the C program. This is real C code. Don't say it out loud. Keep it in, then put your hand up. Do you know, Paul? Yeah, because it's not doing a safe copy, right? It's not copying the buffer, and so if you have a buffer that's longer than that, it's going to copy the whole thing into there, okay? Crashing the server is as easy as we run that De Bruijn pattern, we run that tool on our Linux machine, because Linux can run rec scripts. You run it on your Linux box, I copy the code with Xcopy, and then I paste it into Netcat as my user ID. Okay, so I connect to the FTP server, and then I paste that De Bruijn pattern, and you get a dump of the FTP server, right? This is what the dump looks like. Here's the line that really matters, right? So PSW at the entry to the append, CD948. Okay, so that means that at that memory address, some instruction failed. And we have the dump. So we can look and see what was at that location, right? And if we look at that location, in memory, we see this, 90CE2000. Does anybody know what that is? That's machine code, but does anyone know what that is in Z architecture assembly? No? No one? All right, let's take a look real quick. So we actually have a rec script that helps us decode these machine codes. So once we run it, we get this, store something in memory using, I'll explain it in the next slide. right? So this instruction stores the registers 12 and 13, 14 in the location referenced by register 2. Problem is, we overwrote all the registers. Not just register 14, we overwrote them all. So the program is not returning yet. It's doing other stuff with the registers, but we've told it to go some crazy-ass place in memory that might not even exist. And so now it's dying before it gets to the return. So now we need to start finagling our de Bruijn pattern a little bit, right? So when we look in our dump, for what R2 is set to, it is set to this, which is BH7B. So that's definitely in our de Bruijn pattern, right? But it's outside of memory. So now we got to do something about that. Oh, okay. I got nervous because, you guys see that, right? You guys can read that?
We need 4 bytes.
I did not realize that PowerPoint would make the shadows visible when you have animations. Fantastic. Hey, if I'm asking questions, don't read these. All right. The problem with ASCII, so we have a problem, though. What's that? Okay, so we have a problem. We know in the de Bruijn pattern where we're having an issue, but we can't change it because when we upload the file, the FTP server is translating it back into EBCDIC. So we need to find a byte that when translated from ASCII to EBCDIC is a place in memory that we can go to. That's the problem that I told you it was going to get worse, right? So we need 4 bytes in ASCII that when translated to EBCDIC is an addressable area of memory. Doesn't matter where. We can kind of go anywhere, but it has to be somewhere benign, right? So somewhere that it doesn't matter that it's like, you might point it to a place in memory and it might just be like, oh, I'm doing stuff, and yeah, so it might still crash. Okay, so FTP, our memory starts at 12C000. Anybody see a problem with the zeros? Can't use null bytes in C, right? Null bytes are a terminator. So if we send a null byte, it'll just end the buffer overflow. It'll stop working. Right? We can't use a null, so we pick, it just so happens that in ASCII to EBCDIC, 12 is the same. Hex 12 doesn't change to anything. So we can just use that. I don't care where it goes in memory. We're just going to go 12 bytes in. Who cares? 0C0 is not translated. Like, it does not, it's not the same. So now we gotta set it to 7B in ASCII so that when we upload our file, it gets converted to C0. So now we replace this memory location, 12C000, with 127B12. 80, don't worry about the 80. 127B12. That's where we're going to tell register 2 to point to in our overflow, and hopefully we can continue on. Okay, so this is a way more complicated program. So this is how many instructions we had to get through before we finally branched somewhere off of register 14. Yes, question?
Do mainframes use virtual memory?
Mainframes absolutely use virtual memory. They invented it. Like in the 60s. So this is all the instructions we had to get through until we could return. So now we've done it. We finally found the return register, like what we need to set it to in the de Bruijn pattern, okay? Now it's super easy. So again, register 2 and 13 were problems. Question?
On mainframes, are you still able to use a NOP sled?
The question was, are you able to still use a NOP sled? No, there's no NOP, sort of. But no, there's no NOP sleds.
Well, there is. No 700.
Well, okay. There's no NOP opcode. We'll put it that way. So 2 and 13 we got to deal with. So now we changed the memory locations of 2 and 13. And finally, after all that, right, we get this. This thing is not working. This is what we're looking for. We finally get a return. So the program crashes, and the return is something that's in our de Bruijn pattern. Now we can use that for something. Okay? Again, it's in our de Bruijn pattern. It's 8A C9. That's what we were able to find. Easy mode now. We make some shell code. We change 8A C9 to point to our memory, and we're done. Right? No. Because now we have to deal with the biggest problem of the S. We have got to deal with the ASCII to EBCDIC for every byte in our shell code. Okay? If we look in memory, our memory location starts, okay, that sucks. It starts here, right? We start at 13, 40, 80. Here's what's at that location. That's the beginning of our De Morgan pattern, right? So that's where we're going to start all of our stuff from. But if we use these 3 bytes, it's not going to work because it's getting translated when we send it up. So we have a program in Python that will look up the translation for you. And it just says, yes, question?
Doesn't DD translate this data?
DD will translate it from ASCII to EBCDIC, right? But the server itself also does the translation for the username. So even if we sent it EBCDIC, it's still going to translate it thinking it's ASCII. Right, but that's a great question. Yes, for those who don't know, DD lets you convert EBCDIC to ASCII or the other way around. Okay, so we have a Python script that will find equivalent bytes that we can use now in our shellcode. We're going to use the exact same code, right? We're going to use the same shellcode that we used previously. Really simple shellcode, not very long. Same process. The problem is if you look at our shellcode, it is full of nulls, right? And nulls do not get translated. So there's nothing we can put here that will translate it from a... So now we got a problem. So we have a separate Python script that will take... It will look for an XOR. It has a list of bytes to XOR against. It starts with 99 and starts moving down until it finds a byte that is safe to send and will be translated properly. Because you have to imagine there's lots of bytes that won't get translated because they're outside of the range for EBCDIC. So we have all this stuff to figure that out, written in Python. So it creates, it XORs it essentially with byte 99 for every byte in your shellcode. And now our shellcode is essentially just a key and an XOR value, and we XOR the whole thing against that key to get our shellcode back, and then we jump into it. This is what that looks like. So now our shellcode is going to look like this, right? So we put in our shellcode, we put in the XOR key, and then we assemble this now. So now our shellcode looks like this. This is what, and see all these 99999? So now look, no nulls in here. Perfect, right? We can upload this. Only problem is this is still like EBCDIC bytes. If we try to send this, well, probably need to convert it again into ASCII. So we run the program again, and now it will give us a string that we can use that's in ASCII that when we run it on the... So yes, that was a long way to explain this. I will explain it to you now in pictures for those who have been drinking. We make our shellcode. We find the XOR no null key. We make new on XOR shellcode. We then EBCDIC to ASCII it, right? Then we paste that into our De Bruijn pattern, and then we send it. And when we send it, we get this on the terminal. That means we successfully did a remote code overflow, even though there were so many challenges in the way. Okay?
Is it bad that your pictures hurt my brain more than all your shellcode?
Oh, welcome to the world of mainframe. It all looks like this. All of it looks like this. And if you don't know what you're looking for, yes, and it's all crazy colors. It's great. I love it. But that's because I grew up on like war games and hackers and stuff like that. So, I want to thank the conference for having me. Thank you so much. I want to thank Jake LaBelle for figuring all this out. He's the one who wrote the test. This is all sanctioned, by the way. It's not like I just showed up and Jake's going to find out later. I make sure to ask for permission and I get him to look at the slides, right? Like we're a team. He would have come out. He's like, I was like, hey, you want to give a code talk? And he's like, no. So. Hercules Dev. Hercules is what makes this possible. It is a mainframe emulator that you can run. I can run it in Mac. I run it in Docker containers on GitHub Actions, right? Like it's really cool. Thank you to Jay Mosley for making MVS 3.8J possible. So that means you can all experience the pain and suffering of mainframe hacking from home without having to pay a lot of money. Yeah, and then if this is interesting to you and the mainframe world is something that you would want to get more info about, there's the Moshix Discord channel. He has a ton of talks on YouTube. Just go watch one of them. There's a link to the Discord in one of them. So I hope that this intrigued you, and I hope that, look, I'm always looking for more mainframe hackers because there's only, like I said, 15 of us. So I'm always recruiting members. So if this was interesting to you, yes, they're all dying.
When did the last one die? Rude.
That's actually, I don't know, but we have some pretty elderly gentlemen in that group. We also have a bunch of young people, so it's kind of nice.
Hey, I thought no judgment here.
But any questions? I got 1 minute left. No, I have no minutes left.
One question.
Anyone got any questions? Way in the back. It's starting to fill up, so maybe just come up here and I'll answer it. All right, thank you, everybody.